In this work, we focus on the task of scene graph to image generation. More precisely, we aim to learn a mapping F from scene graphs to images such that an output image respects the constraints of the input scene graph. We focus on the limitation of current models. While for us, the scene graphs at the left seem perfectly identical, applying current models will not necessarily produce the same result. To mitigate that, we present a model that learns to map similar input scene graphs into a single learned canonical representation. This mapping does not require any assumptions and is purely learned from data. By mapping input scene graphs to a canonical form, our model obtains stronger invariance properties. This leads to models which perform better over large scene graphs, generalize better, and are more robust to noise on the input. Given an input scene graph, we start by mapping it into its canonical representation. This canonical scene graph is then fed into a graph convolution network, which is used to predict the layout of the scene. What should be the canonical form of an input scene graph? One natural choice is the relation closure. This is the graph containing all possible implied edges. We deal with two types of completion rules: converse completion and transitive completion. For example, if we know that left and right are converse, then A left to B implies that B is right of A. Therefore, given an input scene graph, we aim to compute its corresponding relation closure, which serves as the canonical representation. To do this, we follow a two-steps process. First, converse edges are constructed. For every edge, we complete edges that are converse to it. Next, we construct missing transitive edges. The procedure described produces the relation closure with respect to converse and transitive completions. This is our canonical representation. In this process, however, we've used few rule-based assumptions. For example, we assume that the relation right-off is the converse relation of left-off. Next, we show how this can be learned from data. Instead of assuming converse completion rules, for every relation R, we can learn the probability that other relation R tag is converse to it. Then, to complete converse edges, we can simply sample from this distribution. Instead of assuming transitive completion rules, for every relation we can learn the probability that it is transitive. Note that different relations might have different degree of transitiveness. For example, if A is near B and B is near C, it is very possible that A is near C. However, this is not guaranteed. To better capture this, we assign completed transitive edges this soft probability. The completed graph is then fed into a graph neural network, which outputs a bounding box prediction per object. The loss is the AL1 loss over the predicted and ground truth boxes. Here are some results of generated images on the COCO datasets. The results demonstrate that the output images produced by our method are rich and capture more complex scenes. To further demonstrate that our model better generalizes to complex scenes, we test the models over such scenes created in test time. We see that while our model can further generalize, the baseline model struggles. Quantitatively, our model outperforms strong baselines which are at least 3 times deeper and have more than 3 times the number of weights. Thank you for joining, and we look forward to seeing you at the QA sessions.